We are established since 1917. It's a family business, starting with small heating boilers, and today, 100 years later, we have already 12,000 employees all over the world. So we have 23 production companies in 12 different countries, and we have a full range of heating solutions. So we don't only produce heat pumps, but we also have solar thermal panels and electrical panels. We have cogeneration systems, so the combined heat and power machines. We have also biomass burners and fossil gas and oil boilers. So we have a complete range. We can select the right solution according to the problem or according to the demands of the customer. So as you can see, it's a little house we drew up here, so we have very different solutions within this house to heat the building or to cool the building. Within inside of this project, the hybridGEOTABS, we are going to discuss the heat pumps, mostly the geothermal ones.
The other arrow.
Okay. So today I'm going to talk about the heat pump design, a bit about refrigeration circuit inside the heat pump, the F-gas regulation that is upcoming, what's the influence of on the F-gas regulation on the different components. Also I'm going to talk about the hydraulics, how is a heat pump integrated in the building, which are different solutions and working conditions. Another aspect is the natural cooling, we saw it in the presentation of Hectro. And then we have the domestic hot water, also a very important part of the building. Now, how are we going to select the correct heat pump? First, we have to know the building, the size of the building, the heating load, and then it's very important to know the working conditions, because the power output of a heat pump is always given at norm conditions. So that's at the B0 W35, that means that the input temperature to the heat pump is 0 degrees. So out of the source comes 0 degrees, and the output on the secondary side is 35 degrees. If we look at this table, we have a heat pump from Viessmann. The animation is not running. So I wanted to show you the working point, 0.35. We have 84.8 kilowatts of power and the COP of 4.6, 4.7. When we change the input temperature, as we saw from the geothermal source, is about 10 to 50 degrees. You can see here that the output power of the heat pump changes also, but that means also that the cooling power on the primary side, on the evaporator side, also changes. And the COP goes up. So when the COP goes up, we actually use more energy from the source than at the norm conditions. So that is very important to know on which condition is the heat pump going to run, to know exactly how much power am I going to use from the source. Even now, for concrete core activation, Viessmann added a new table, so we test the machines on different working conditions, and we add the table of the source at 0 degrees and the secondary side at 25 degrees. Because for concrete core activation, the temperatures on the secondary side are mostly not higher than 25 degrees. We're going to see that later on in the next presentation. So you can see the same heat pump here at 0.25 gives a little bit more power, but the COP here is a lot higher. So we have 5.8 in comparison to 4.6 there. Even here you see when we have an input of 10 degrees and we have 25 degrees departure, on the secondary side we have a power of 112 kilowatts for the same heat pump. Now, another aspect of selecting the heat pump, especially in a hybrid system, is that we can select the heat pump not at 100% of the demanded power. You can select, for example, the heat pump at 40%, 60, 80 or 100% of the total power. What does that mean in running hours, and what's the effect of this selection on the primary source? Therefore, we have a curve, you can see it here. This one is the parallel working curve, so it means that the gas boiler and the heat pump work together. This is the alternative curve. This means that when the gas boiler starts to work, the heat pump will stop working. There are the two differences you can see here. Mostly we will work in a parallel condition, and if you see, with 40% of the power, so if the building has 100 kilowatts at -10, for example, with a heat pump of 40 kilowatts, we can cover almost 80% of the total heat load. So that's very much in the total. Even if you go up to 80%, we can almost reach a coverage of almost 100%, so about 96% of the total demanded heat. So I have made a small example, so like the heat pump of 40 kilowatts and 80 kilowatts, and both will be placed in a building with a demand of about 100 kilowatts. And we will see when we calculate the running hours for both systems, that's very important to select the right source. So, for instance, I calculated 1400 hours of total running in a new building. I think it's realistic because it's good insulation, and the running hours are lower than in an older building. So in a total year consumption will be about 140,000 kilowatts per year. And if we see here at the curves, we can see that a heat pump of 40 kilowatts can almost deliver 80% of the total. So that means that the heat pump there will deliver 112,000 kilowatts of the total energy needed for the building. In the other case, with the 80 kilowatt heat pump, we will deliver 133 kilowatts by the heat pump. So this means that the heat pump, the small heat pump of 40 kilowatts, will actually run 2,800 hours. That's double the normal calculated running hours. So 1,400 hours in full power means at 40 kilowatts that we will run 2,800 hours per year on this heat pump. When we have the heat pump of 80 kilowatts, we will have 1,662 running hours. What does that mean on the source? So I first went with the normal conditions, the normal condition of a COP of 4.6 in this example, because you saw it in the table at the beginning. So that means with these running hours for the two heat pumps, 40 kilowatt heat pump on the secondary side with a COP of 4.6 will use 31 kilowatts on the evaporator side. So that means that when the running hours are 2,800, we will deplete the source with 87,000 kilowatt hours. That's actually a lot. That means that it's actually 80% of the original sizing. So it's very important to not make the mistake, oh, I have a heat pump, it's only 40% of the total heat load. I will make the borefield only 40%. So then we will have a problem during the heating season. You can also see that at 80 kilowatt heat pump, also with a COP of 4.6, we will almost be at 95% of the original size of the source. So that's very important to know that when you select a smaller heat pump, the running hours will be much more than normal with a 100% selection, and that we will use the source in comparison here 80 and 95% of the original size. So when selecting a smaller heat pump, calculate the source based on the running hours and not on the power output from the heat pump. That's a very important conclusion. A small part about F-gas regulation. I think you all know a bit about that. That's a bit of a problem today. So we have the global warming potential of the refrigerants that we use today. And there has been an agreement that says we have to decrease the global warming potential. And that starts from a baseline set here in 2015. So we had 100%. That means that if a producer of heat pumps places on the market 1,000 heat pumps per year, his total global warming potential for those 1,000 heat pumps is X. That means that in the future he will go down in his total global warming potential by 2018 only 63% of the original. And if you think logical, today we sell a lot of gas boilers and heat pumps are upcoming. So that means in the future we will have to be, with all the new heat pumps that are coming, we have to have a lower GWP than we had in total in 2015. So that's a challenge. We have to see how we can do that. If we see 2021, that's not so far away. It's only 45% of the original. And then in 2030, only 21% of the original is allowed. So we have to develop some new refrigerants to meet this demand. Which are the refrigerants we use today? Today, Viessmann uses R410A in the larger geothermal heat pumps. We also have heat pumps with R407C, and we have smaller heat pumps with R134A. These we use mostly in the heat pump boilers for domestic hot water, and we are starting to change this refrigerant into the 1234ZE from this year on, normally from August. What do we see on this graph? We see that the R410A has a GWP higher than 2000. And everybody knows what it means, GWP. So if we let escape 1 kilogram of this refrigerant, we have a CO2 pollution of more than 2000 kilograms. See, that's very high at the moment. What's the development that we see today? So the benchmark for 2018 lies here. So we have a number of different alternatives. One alternative used by Daikin, for example, is the R32. R32 is a refrigerant that's already present in the 410A. 50% of 410A is R32. So it's a refrigerant that is well known and can be used today, and it meets the regulations of 2024, for example, you see. But what's the main conclusion? The refrigerants that are here in this sector are just a temporary solution. When we go to the set point of 2030, they will not be able to use these refrigerants. So we have to go to even better refrigerants, such as the natural refrigerants, or R290, which is propane. That's a refrigerant that can be used. It has a very low GWP, and another refrigerant that is upcoming is a 1234ZE or YF. We are using this refrigerant in a special heat pump designed by Viessmann, and with that heat pump you can work with source temperatures up to 50 degrees, and you can make secondary temperatures up to 90 degrees. So in the future, when we have a need for high temperatures, and we have a waste heat source of about 40-50 degrees, we can reuse that waste heat to make a very high temperature and supply another industrial process or a heating demand in a building. So this is quite a challenge, because what we also see with the different refrigerants, the refrigerants we use today we know very well. We know the components we use, the compressors, the evaporators and so on. But when we use more natural refrigerants or other refrigerants, we have to adapt also the refrigerant cycle inside the heat pump to work with these new refrigerants. So you see here the 410A has a GWP of 2088. The maximum depart temperature we can make with this heat pump is about 60 degrees. So, and you see the COP of this system is about 4.6, such as we showed in the table. Other refrigerants used today, R32 also has a very high departing temperature of 60 degrees on the secondary side, and the COP is comparable to the R410A. When we look at other newer refrigerants, the HFOs here, you see that the COP is a bit lower, but the departing temperatures on the secondary side can be much higher. That's really interesting. If you look at buildings where we want to make domestic hot waters locally in each apartment, you have to have the option of a higher departing temperature. So in the future, we have to be below the GWP of 10. That's very important. So if you see only propane is ready now, and the two newer refrigerants here are ready. This arrow indicates the power density of the refrigerant. That means that we go higher when we go in this direction. So 410A means we have to make less flow of refrigerant for the same power output than, for example, with the newer refrigerants. That means that when we use these type of refrigerants, to get the same power output, we have to use larger components, bigger compressors, to move more refrigerant through the cycle. That's something very important. And also what we saw on the previous slide is the flammability. So we have the green ones are non-flammable. Then we have the newer refrigerants are mildly flammable. So we have to have special measures in the technical rooms. And if you see at the propane, it's highly flammable. So this is oftenly a heat pump that has to be placed outside the building. So that's a bit how we stand today. So a conclusion on the F-gas regulation is that the GBP has to decrease. It will decrease gradually. Today, less than 2,100, and in the future, less than 700, and even less than 150. This makes refrigerants more flammable, so increased demands on technical and machine rooms, and more heat pumps will be installed in the outdoors. Efficient heat pumps are also possible with low GBP refrigerants if you have the right components inside the machine. Here again, a table from the heat pumps we sell. So we have different output powers, 90 kilowatts up going to 230. We see that all these machines work in two-stage compressors. So it means we have two compressors in one refrigerant cycle. So we can control the output power in two steps. For example, at a 90 kilowatt, it will make about 85 kilowatts on two stages. And when we switch to one stage, it will be about 40-45 kilowatts. So this is one way of regulating the power, but a very important aspect is also the flow rate on the evaporator side of the source. So the mixture of glycol in the source is flowing through the source, but also through the evaporator, and we have to maintain a minimum flow. So you can see here, we have to calculate the flow rate, you have a nominal flow rate of about 20 cubic meters per hour in this example, but the minimum flow rate is not half of this. So it's not because the heat pump switches to maximum power and half the power that the flow rate is going down by half. That's very important. It's about 75% of the initial flow rate that you can see here. That's the minimum flow rate, and why that is I will show you in the second slide. What can happen if the flow rate through the evaporator is too low? Then we can have that the refrigerant is not evaporated completely. As you can see in this thermal picture, the refrigerant is going through the evaporator in this direction, and the flow of glycol mixture is going in this direction. And what do you see? That in this case, the flow rate was too low, and we have liquid refrigerant going to the compressor. And that has to be avoided at all costs. So what will happen here? The electronic expansion valve will detect the low temperature here, and it will close off. So the power that is obtained from the source will be much less. We also have a test here. You can see it's about SWAP is the constructor of our heat exchangers. They did a test with water, sprinkled water onto the system, and you can see the freezing pattern according to this picture here. They also added a special device inside the heat exchanger to equalize the flow of refrigerant throughout this evaporator, so you have a much more stable flow, and that means that we have a better working of the heat pump. So it's very important that when you select a heat pump and you calculate the evaporator flow rate, that you keep in mind that when the heat pump is a two-stage heat pump, that you keep in mind the minimum flow rate of about 75% of the normal. What we also see today is that we use asymmetrical evaporators. This means that the size on the refrigerant side is much smaller than the size on the liquid side. That is also a benefit to the total refrigerant load inside the heat pump, inside the refrigeration cycle. And that's a good thing for the F-gas regulation. We use less of refrigerant, so the GBP of the total concept of the total heat pump is lower. That also means that we have lower energy consumption of the primary pump, because the flow through the evaporator will be easier. The spacing between the plates is bigger, so it will flow much easier. And that effect is even bigger when we use glycol, because it has a lower flow rate. So that's a development that we see today. You can see the channel volume on the refrigeration side, and you can see the channel volume on the water side. Something about compressors. Which types of compressors are often used? Do you know that? Mostly we use scroll compressors, I think. And then you have an option of the reciprocating compressors with the pistons. Why do we use scroll compressors? So, two types commonly used, scroll or the scroll compressor. What are the advantages of this system? It's cheaper to produce, easier to make. It is space saving because the compressor is built in the height, more efficient, and can be used with efficient high pressure refrigerants such as the R410A, which we use today, and also a newer one with a lower GWP can be used in this type of compressor. The disadvantage of this system is that it cannot be repaired. So when we break the compressor due to liquid inside the compressor, we have to change the entire compressor, or when the electrical motor gets burned, we have to replace the total system. It's also not suitable for high temperature heat pumps because they work with a fixed delta P. So the pressure difference over this type of compressor is fixed. It's depending on the suction pressure from the evaporator, and then it's a fixed increase of pressure to the condenser side. That's also negative sometimes when the condensing temperature is a bit higher, that we have an under compression in this type of compressor. That's something that can happen with this type of compressor. That's not so very bad. Another type is then the reciprocating compressor with the pistons, also from Bitzer here in this image. It's a commonly used compressor because it has a lot of advantages. It's repairable, it's suitable for high temperature heat pumps. It's built more robust, so it means it can handle more load, let me say, or more running hours. It's used in CO2 applications with propane, or the R1234ZE or YF use these type of compressors. Also, the pressure on the condenser side is always right. And why is that? Because this compressor has valves inside, and the valve will only open when the pressure underneath the valve is higher than the pressure in the condenser. And then we have always the right condensing pressure that leaves the compressor. The disadvantages is that it's more expensive, and it's only suitable with low volumetric refrigerants except CO2, and it's not optimized for high pressure refrigerants such as R410A. That's the reason why we use mostly at the Viessmann heat pumps today, the standard heat pumps, we use the scroll compressors. Another development that I saw at Danfoss is the new type of turbo compressors. It's like a hydraulic pump. The principle of it is like a hydraulic pump. We suck in the refrigerant into the compressor, and it works with a lower delta P, but with a high volume flow. So it's typically for the hybridGEOTABS project, where we work with low temperature differences between the source and the condensing side. This can be a very interesting type of compressor, also for the newer refrigerants. So that's something we will look at in the future. Danfoss has developed a turbo core, and it's in development since 2017. What's the working envelope of a compressor? Why is that important? So I have an example of a working envelope of the compressor, a scroll compressor from Viessmann. What can you see here? This is the input temperature on the source side. This is the secondary temperature on the condensing side. And what do we see? That when we have, for example, a source temperature of 0 degrees to about 10 degrees, the minimum departing temperature on the condensing side is 25 degrees. So you cannot go lower than that. That's because of the fixed pressure differences between the evaporator and the condensing side. Even with higher temperatures, like above this 10 degrees, 15, 20, we see that the departing temperature in the condenser has to be much higher because the input pressure is already high. You see. What you can see in this envelope is also with source temperatures of about 5 degrees, we can reach the maximum departing temperature of 60 degrees. This is what you can see on the top. So for the GEOTABS project, for example, I have added these two lines. So with a departing temperature of 25 degrees, we can work without a problem with source temperatures of 0 to plus 10 degrees. So that's a bit the changing point. Higher than plus 10, the secondary temperature will rise, and we will have to find a solution. For example, work with a buffer tank so that we can keep the compressor running and that we regulate the temperature after that. Now, what's the influence on working in these regions of temperature? 0 to 10 with a departing temperature of 25. This line you can see here. Above 0 degrees, we have a COP that's actually higher than 6. See, we go up to 6.5, 7 and more. So it's a very efficient working zone, but it has its effect on how we calculate the source side. These are other envelopes of different refrigerants with other compressor types. They are mentioned here below, different refrigerants, different compressor types. You can see that the power output and the displacement, so the heating capacity is much lower with the 407, for example, in this case, but it's just an example of different working envelopes that we can use, and we have added also the one of propane inside this example. So what's the influence on the source? If the COP increases, the load on the primary source will also increase. This makes it important to know the working envelope yet again, because we have to know the COP of the system, and then we can effectively calculate the load on the source. So if you see here in the example, the first calculation was made with a COP of 4.6. In this example, I took the COP of 6, and you can see that with this higher COP, the source, the load on the source is increased and even is higher than originally calculated. So you have to know the COP or the working conditions of the compressor to make a correct calculation of your source. That's very important. So I talked a bit about power control. So you have a system with fixed speed compressors. You can have one-stage or two-stage compressor. You keep in mind the minimum evaporating flow with the two-stage system, and also the sizing of the buffer tank is important. Normally, when we size a buffer tank, we use 20 liters per kilowatt. So if you have a 100 kilowatt heat pump, you have about 2000 liters of buffer tank. If you have a two-stage compressor, you can select the buffer tank on the minimum stage, so the lower stage of about 50 kilowatts, for example. And why do we do that? That is to have a minimum running time of the compressor. It's very important that the compressor is not switched on-off, because it will wear the compressor down much faster. Also mind that when you use a one-stage compressor, you have a much higher start current. In Belgium, for example, a building or a company is charged on these peak currents they use. So when we can keep the peak currents low, it's better for the energy bill. Less suitable for building loads, because we see in the diagram in one of the first slides, you saw that with 40 or 50% of the power, we can almost cover the whole year. So you don't need 100% of the power that often. You will run more on the first stage of a two-stage compressor. So that makes it more suitable to follow the building loads. A newer development is inverter controlled compressors. So when we can regulate the rotation of each compressor, you can see it's very high in COP. The part load COP is very high. We have much more longer running time, so that's much better. And we have less starts. Another benefit of this system is that we have, when we have solar panels, we can easily use the energy produced by the solar panels instantly. We can follow the load on the production of these panels. And other side of the inverter control system is that we have a standby loss by the inverter, which can be up to 4% of the electrical load. Now, what's the influence on running on two compressors on one compressor? It's often thought that when we run on one compressor, we have a bigger evaporator, so the COP will be higher. We have done a lot of tests in the field, at our laboratory also, and you can see that it's not that big of a difference. So Here you can see a stable running machine. The flow through the, I think it's the compressor, the condenser here is shown here. So it's a stable flow, and you can see at this point we switch from 2 compressors to 1 compressor. It has a small peak in COP, but that's just because the power change, that's to be calculated. And then you can see the COP rises a bit, but then it will stabilize in time at the same point as it was before. See here. So it's not that big of a difference if you run on 1 or 2 compressors. So it will stabilize, and a part of the explanation here is that we have a fixed superheat. The evaporator, the expansion valve is regulated on a fixed superheat, and that's part of the explanation why the COP doesn't change that much. So this is another difference where you can see the part load, and you can also see that the COP here, when switching from 2 compressors to 1 compressor, in time will be about the same COP. What's the influence of the delta T? I didn't speak about that yet, because normally we use a delta T on the condenser side of about 5 degrees when we work with a buffer tank. When we make it bigger or smaller, you can see that here, this is the delta T, for example, on 2 compressors, the condenser side, evaporating side, and then the delta T, because the volume flow is fixed, decreases. But with a smaller delta T, it also has the same effect on the COP as showed previously. So it stays about the same. What is really important is to keep the departing temperature of the heat pump as low as possible. We can see here at the evaporation temperature, when we have a difference of 1 degree or 1 Kelvin, we have a gain of about 2.7% in COP. For example, you can call that a rule of thumb. On the condensing side, it's a little less. When we can reduce the departing temperature in the condenser, we gain about 2.5% in COP. So that means when we have a temperature that's 10 degrees higher than necessary, we lose about 25% of efficiency of the system. Then a bit about hydraulics, how to connect a buffer tank. There are many visions. We have done a lot of tests in the field, and we see that some systems work better than others. This is the usual way we use it in domestic applications, small buffer tanks. So the input from the temperature is on top, and the departing temperature to the installation is here. Return from the installation, return to the heat pump. What we see with bigger installations, we have high flow rates. You get some mixing of temperature during this process, the transfer here, and that means that the temperature is often lower at this point than at this point. So what will happen? The heat pump has to make a higher temperature here to reach the demanded temperature to the installation, and that means, of course, a loss in COP. So what do we do today? This is one of the schematics we use today in the larger applications. So the heat produced by the heat pump is immediately transferred to the installation. Only the excess flow is put through the buffer tank. And then you can ask, why not do it like this? This can give some problems. When the pressure drop over this side is lower than through the buffer tank, sometimes that can be, this is a schematic, but we have a lot of turns and things, that can be a problem. Then we see that the buffer isn't discharged. So when the temperature sensor is sitting inside of the buffer tank and it's on temperature, the heat pump won't switch on. We have just a flow through the evaporator, but the heat pump thinks, oh, the buffer is on temperature, I have to do nothing. So then we have to add a valve which regulates the pressure drop on this side, or we use this system where all the return water has to pass through the buffer tank, and so it will discharge the buffer tank correctly. Another thing to mention is that the speed at which we enter the buffer tank has to be lower than 0.3, 0.4 meters per second, because if you go over that speed, we get a mixing inside the tank, and that's not correct. Here you can see different delta T's we use. So I spoke about the delta T of 5 Kelvin on this side. So we have 30 return, 35 in the buffer tank. Through the installation we have a departing temperature of 35 degrees, but here we work with a higher delta T, so a lower flow on this side. And we see that we charge the buffer tank when it is full, the compressor will stop. So we need this buffer tank to get a separation between the two pumps. This pump and this pump have to be hydraulically separated, and we use the buffer tank in this case, because of the different delta T's we use, for a minimum running time of the heat pump. How do we make a hybrid installation? In my eyes, a hybrid installation is an installation combined with a gas boiler, for example. So when we have a heat pump of about 40% of the total load, we need another device that can cover the other 60% when needed. So in this case, how do we couple the two systems? In the picture, or the schematics here, you can see the heat pump is connected to a buffer tank on the underside of the buffer tank, and we have a gas boiler or oil boiler or something else. It's connected on top of this buffer tank. The risk we have here is when the gas boiler begins to work, is that the gas boiler will heat the total buffer tank. And then the heat pump will also think that it has nothing to do, and the heat pump won't start anymore. So we have another type of schematic that we use, and that is actually the heat pump is connected to the buffer tank, and after the buffer tank we have a mixing valve that mixes heat out of the gas boiler when needed. And the control of that mixing valve is done by the regulation inside the heat pump. So the heat pump will measure the temperature here. It will see if the temperature is as demanded, and if the temperature is too low, it will activate the gas boiler and then control this valve to mix extra heat into the departing line through the installation. You can also work with this type of system. That's another option. It's not used by us. I mentioned how it is controlled. There are some smart regulation inputs inside the system to prevent that the gas boiler is activated too soon. Another source of energy is solar energy, for example. Here we have solar panels, thermal panels, which charge a buffer tank here, and this can be discharged to the buffer tank also from the heat pump. So we can use a clean energy source as well. This is biomass, for example, this has its own buffer tanks, because there it's different. We have 50 liters per kilowatt up to 100 liters per kilowatt, depending on how the biomass system works. Natural cooling is another aspect that we can do with the geothermal source in this project. So we have a heat exchanger here connected to the source, and with this heat exchanger we can circulate temperatures of about 10 degrees, for example, throughout the building. Sometimes we have to use a cooling buffer tank. Mind the connections here, it's not like a normal buffer tank, sometimes that's done wrong. So that's an option. We can also control the temperature to the building with a mixing valve here, because the source temperature can be 10 degrees, for example. If we send 10 degrees to ceiling systems, we have condensation, so that has to be avoided, and we can do that by this mixing valve. So that's an option. Then finally, domestic hot water. The maximum supply temperature is depending of the refrigerant type we use, and also the return temperature inside the system. And the COP, of course, is also depending on the supply temperature needed inside domestic hot water tests. There are many different systems that can be used. So here you see the heat pump with a normal buffer tank for the heatings, and then we have a plate heat exchanger to load domestic hot water inside the buffer tank. You can control this pump by control of speed, for example, so you have a higher charging temperature, or we can use a mixing valve to regulate the charging temperature in this example. This is an off position, so it means that we make heat for the building, or we are charging the domestic hot water tanks. Decentral can also be used, so if you have a building with a lot of apartments, you can send the temperature throughout the whole building for heating, and then when one buffer tank asks domestic hot water, then we have to increase the temperature, so that automatically happens when the return temperature increases, the departing temperature increases, and we can load a boiler, a decentral boiler. What also exists are these type of heat pumps, booster heat pumps. They use the low source temperature here, 35 degrees for example, or the return temperature, and they can use this source to make a higher temperature to load a decentral boiler. There are some different system types. If you want to charge at higher temperatures, you can use this mixing valve to increase the temperature, the return temperature in this case, so that the departing temperature also will increase. So you can load the buffer tank a bit higher. This increases the comfort of the domestic hot water because hot water is quickly available. We also have another system without this valve, but then we use a PWM controlled circulation pump. Here you can see some temperatures, why it's important not to charge the domestic hot water tank on top with a normal system, because when we have a return temperature of 28 degrees, the departing temperature is only 33 degrees. And when you inject that on top of the buffer tank, it gives a problem in the domestic hot water production, of course. So there are some different systems. Also we speak about a maximum flow rate of 0.1 meter per second on the incoming side to keep the stratification inside of the tank normal. We can use this type of pipe also inside. It deflects the incoming hot water in a plane, so it will keep the stratification correctly. So now the next speaker is Qian, I think. He will talk about the depth side of the project, so the distribution of the heat produced by the heat pumps and delivered by the